This is a background gamma level. Cesium 137 source. The large aluminium block behind the source leads to an increase in measured gamma radiation level. We measure a 25% increase in gamma radiation level when there is a large aluminium block behind the source. This seems a strange phenomenon. The gamma rays that travel opposite to the detector would normally remain undetected. However, with the large block they appear to be partially reflected. To see what's happening, let's take a look at the gamma spectrum of Cobalt 60 and Cesium 137. This is an LBC scintillator connected to gamma spectacular. Which has a USB connection to an external sound card. Use PRA software on the PC to register the spectrum. To peak at 661.6 kilo electron volt emerges immediately. Spectrum becomes nice and smooth after some time. We now put the large aluminium block behind the cesium source. The spectrum with the large aluminium block in position shows an extra peak. It is due to backscatter of the gamma photons and located around 210 kilo electron volts. The small insert shows the previous spectrum without the aluminium block, showing only a tiny backscatter peak. Now we switch to the Cobalt 60 source. Its characteristic photo peaks at 1173 and 1332 kilo electron volts rise quickly. When a scattered gamma photon escapes from the crystal, only the energy deposited on the recoiling electron is detected. We repeat the measurements with the aluminium block behind the cobalt source. And just like with the cesium source, the block of aluminium leads to a large backscatter peak. The insertion shows the earlier spectrum without the aluminium block, with only a small backscatter peak. Now let's take a closer look at the so-called Compton scattering. A photon of frequency nu, the Greek letter, collides with an electron at rest. Before the collision, the energy of the photon is given by Planck's formula. Upon collision, the photon bounces off the electron, giving up some of its energy, while the electron gains momentum. However, the photon cannot lower its velocity, so the loss of energy by the photon shows up as a decrease in the photon's frequency, or conversely as an increase in its wavelength. The change in the photon's wavelength is delta lambda, and the electron gains the momentum lost by the photon. The maximum change in wavelength for the photon occurs when it transfers as much momentum as possible to the electron. That occurs at a collision angle of 180 degrees. And since cosine 180 degrees is -1, the maximum wavelength shift of the photon can be calculated using this formula. When we fill in the values, we get a maximum shift in wavelengths for the photon. Now let's go back to the gamma spectrum of Cobalt 60. We can use these formulas to calculate the position of the backscatter peak and of the Compton edge. I used an Excel spreadsheet to calculate these values. We put the energy of the first photon peak of Cobalt 60 in the first field, converting electron volt to joule. We obtain the photon's frequency by dividing its energy by Planck's constant. We obtain its wavelength by dividing light speed and its frequency. Since we know delta lambda, the new wavelengths, the new frequency and the new energy of the photon can be calculated. And thus also the position of the Compton backscatter peak and the Compton edge. Now let's take a look at the second photon peak of Cobalt 60. The photon's wavelength shift, delta lambda, remains the same because it's independent of the wavelength of the incident photon. Also, the Compton backscatter peak is at the same position. Let's go back to the spectrum and display the calculated values. The Compton edges reside at a distance of 210 keV of their respective photon peaks. The electrons at the Compton edge gained the maximum possible amount of energy from the incoming photon that bounced back on them at 180 degrees, and this photon retained only a small amount of its original energy as visible in the backscatter peak. No energy can be lost during the collision. The position of the Compton edges can thus be found by subtracting photon peak energy and backscatter peak energy. These experiments nicely show the wave-particle duality of electromagnetic radiation. Photons are a stream of quanta that sometimes behave as a wave and sometimes as particles. In this experiment, the gamma photons behaved as a stream of particles colliding with the electrons, and they transferred momentum to the electrons. Arthur Compton was awarded the 1927 Nobel Prize in Physics for his discovery